Hello everybody, welcome back to another Gregorius maths video, and I know that it's been a long while since my last video, apologies, but happy December, you know, December, Christmas type time, you know, that's all about forgiveness and such, so yeah, let's just forget about that, and I was going to talk about what I've been learning while I've been gone in algebraic geometry. And hopefully I'll just upload a quick burst of videos basically on topics I've been learning in algebraic geometry. So basically I took a step away from Vakil. I will come back to Vakil maybe later, but right now I'm learning from a book called Basic Algebraic Geometry 1 by someone whose name I forget. And it looks at varieties in projective space, and so right now I'm learning about basic notions, and more specifically what I'm learning about is, you know, algebraic plane curves. And so in this video we're literally just going to take a look at what they are, you know, what we want to study in algebraic geometry, and yeah, you know, just stuff like that. I'm not going to delete the video on sheaves, but it's basically disconnected from this new approach I'm taking to algebraic geometry. So it's part of the learning journey, but it's not part of this path, if you see what I mean. So yeah, this is just going to be 1.1, and then I'm going to make, eventually, you know, when the time's right, I'm going to make another 2.1. That's just not going to be about sheaves, that's just going to be about, whatever, affine space or whatever. So, okay, so an algebraic plane curve, so the first thing that we want to look at, and one of the main things we'll be studying, is the following equation. An algebraic plane curve. So what is it? Is polynomial, we'll say, satisfying the following: f of x, y equals 0. And our coefficients can be in any field k. We'll put f in k of x, y. But really what we're going to see soon is that k is our intuition and, you know, notions that we want to define. For example, the degree of such a curve only really works if k is algebraically closed field. So we'll talk about that in a second. Another important definition that we're going to be using throughout the series again is the affine plane, which is noted with Math BBA. Now my Math BBAs are not great, so I apologise in advance. That's not too bad actually. A2 is just the set of all A, B, with A and B being in K. So it's just the set of all these points. I think that there's a version where you write a subscript K here, but it's clear enough like that. So that's another important definition, and of course note that these polynomial rings, for example, are UFDs, I believe. And so our curve f equal to 0, if we have f equal to 0, then f is equal to a product of irreducible different curves with all of these fi equal to 0. And so in this case this is just, for us this is our algebraic curve being a union, algebraic plane curve being a union of irreducible plane curves. It's like such. And so yeah, okay, so these are just, you know, basic notions that we're gonna, you know, be talking about throughout the series, not just in this video but throughout the series. And so the next thing I want to talk about, and again this is important, is why do we want k to be algebraically closed? Well, okay, let's take a look at perhaps the most natural non-closed, algebraically non-closed field to be looking at, and that is of course the real numbers. Now if we take a look at something like this in the real numbers, for example if we take a look at x squared plus y squared is equal to 0, the degree of this should be 2, no? You know, this binomial is of degree 2, and we want the degree of the curve to be the degree of the binomial, so let's go ahead and say that's 2. But, hold on a second, that's just a point, right? That's just, you can think of that as a circle with radius 0, that's just the origin. But that differs wildly from my intuition. Not only that, but also we have x to the 4th plus y to the 4th equals 0, doing the same thing. In fact, x to any even power plus y to any even power equal to 0, these are all going to just be points. But they should have different degrees, and so on and so forth. And so we pass to an algebraically closed field. So if we have some algebraically non-closed field, k0, and we want to study it, normally what we're going to do is we're going to pass to an algebraically closed field, which for the case of the real numbers is usually going to be the complex numbers. Okay, I might as well give some examples of other algebraically non-closed fields where we want to pass to other closed fields. So for example, if we have k0 equal to the rational numbers, well, this is also important. For example, Fermat's last theorem asks us for solutions of x to the n plus y to the n is equal to z to the n. Or x to the n plus y to the n equals 1 is important, for example, with rational coefficients. You know, there's plenty of different things in the rational numbers which are vastly important, but obviously that's not an algebraically closed field. And so there's another one which we want to study. Another one which is important is the integers mod p. That's another important algebraically non-closed field which we want to study. A good one and a fertile method, apparently. I don't know anything about this, but apparently fertile method for studying algebraic surfaces is with the field of is talking about the field of rational functions with coefficients in C. So if we have k0 is equal to C of z, and what we want to do is we consider some f of x, y, z equal to 0, where f has got complex coefficients, and it's some trinomial with complex coefficients. Then what we consider this as is we consider kind of z as a, you know, constant type thing. And so we consider it as a function in 2 variables with coefficients in rational functions, or not rational, you know, yeah, maybe rational, and some sorts of functions of z. And so we consider this in C of z of x, y. This is where we're working, and apparently, again, according to the textbook, I don't know if this is actually true, this is a fertile method in studying algebraic surfaces and stuff like that. So there's plenty of examples of algebraically non-closed fields which we want to study. And to do so, because of these ill-defined notions, when we look at them in, for example, the degree of a curve, when we look at them in algebraic non-closed fields, we want to pass to another closed field. But anyway, okay. Another good thing about closed fields is that they're infinite, so these curves are going to be infinite too, and they're going to be also unique up to some sort of multiple, I believe, and so they just have these nice properties like that. So Okay. Now we're just going to talk about some stuff which we know is true but only works in non-closed fields. And then we're going to give an example of getting data in a non-closed field from passing to a closed field. So, okay, so Vezoot's theorem states that the intersection of two curves, the amount of intersections of two curves is equal to the product of their degrees. So, for example, if we talk about conics, and conics are algebraic plane curves of degree 2, then there's plenty of things that could happen. We could have this, where they intersect twice. We could have this, where they... No, hold on. Or, hold on, I'm just going to give two cases here. We could have this. They intersect 4 times, which is what we want. So these two examples differ, but why is that? And again, these things only really hold if we're working in... Oh, a good example of Vezoot's theorem is if we're talking about a polynomial, y minus f of x is equal to 0, and y equals 0. So basically the roots of some polynomial f of x. Because that's just the intersection with y equals 0. And this obviously the number of roots of a polynomial being equal to, because 1 times that is, yeah, the number of roots of a polynomial being equal to the degree of that polynomial only holds in algebraically closed fields. So there's another example of failure of things we want to be true. Okay. Here's a final thought for this video. So let's think of a real concept here. Say, for example, the polar line. And what this is, if we have a circle, and we pick a point P outside of the circle, we draw the lines of 2 lines that are tangent to the circle and hit P. Well, anyway, as I was saying, there's 2 points of tangency where the lines will hit the point of tangency and then hit P, and the line that connects those 2 points is called the polar line of C, which is where C is the circle, with respect to P. Now, that's a purely real thing, right? Well, this has, you know, algebraic definition, you know, blah blah blah, and so it also works for P being a point inside the circle. But now these lines are going to have to be like we're not going to be able to see this on the picture. These are going to be complex lines here. And so, I'm not really sure how to draw this, but essentially the idea is that these points of tangency are going to be complex conjugates, and so the line that joins them is still real. And in fact, it's even not even that difficult to define the polar line when P is inside. In fact, I believe it's the locus of points such that their polar line goes through P. And so that's just, okay, that's a very elementary, but I like it. I like that example because it's nice and geometric. And that's what, you know, one would think that we're dealing with, you know, all circles and, you know, tangent lines and stuff when we're talking about algebraic geometry. And so I quite like this approach. And in the next video, I'm going to be looking at rational maps and you know, parameterizing curves and stuff like that. And it's interesting stuff. It is very interesting stuff. So I hope to, you know, go through basically what section 1 is. So the book 1 is split into 4 parts, you know, each with like a few sections. And so I'm going through a first section now. And hopefully once I've done that section, which basically talks about these types of curves in different ways, you know, I'll be able to have a video doing exercises on that section, which will come at the end, and then do the same thing for section 2 and so on and so forth. And hopefully I can make my way through this. Again, I apologise for the long wait for this video. But yeah, thank you guys for watching. Hopefully I'll be back soon, and yeah, have fun. Goodbye.